Hello. Our inspirational and motivational example suggests that also today we will look at algebraic equations that cannot be solved analytically, that is, using algebraic operations and similar tricks. And again, we will turn to numerical analysis for some tools that would allow us to identify, approximate solutions of such, let's say, not very friendly equations. And what we did previously is that we took all these equations and we changed them in such a way that there was 0 on one side. So we move everything to one side, there will be 0 left on the other side. In that way, it transforms into a root-finding problem. However, algebraic equations can be written in many ways, and today we will prefer a totally different way of writing them, namely this one. We want to see x on the right. So when somebody gives us an equation, we rewrite it in this way, and then we have x on the right and some expression on the left. And again, this expression, that's the function that we will focus on. And we are not using f, we are using phi to emphasize that this is definitely not the previous approach with roots. Okay, this is a new situation. Now, we are looking for number x, which satisfies this equation. And when we think of phi being a function, we are actually looking for a very specific number. Let's have a look at a general mapping picture. So typically we would draw the starting set, the ending set, and then somehow suggest how the mapping acts, how it sends objects. Now in this case, the starting set will be real numbers typically, or a subset of it. So we have real numbers, a specific copy of real numbers, and perhaps there is some domain for the function phi. Then there's the target space, again another copy of real numbers. And now the function phi sends numbers from the starting set to the ending set in some way. We don't really know now because it's a general function phi. And we are looking for a very specific number, a number which has the property that when we put it into our function, which means we send it over, it stays the same. It gets sent to itself. And one possible interpretation of this situation is that the function phi is actually transforming the real line. We may have some objects here. Well, this is just a one-dimensional situation, so let's say we have some intervals there, and they make a nice picture. And then we take the function phi and we transform it so the picture changes. So phi is a transformation. And we are looking for special points that do not get changed by this transformation. They stay fixed. And that's exactly the name of this point. That's why there is this little subscript f. This means fixed. Let's have a look at the official definition. So we have a function, and we are looking for points xf, so that when we substitute them, the output is exactly the same as the input. Now, the great advantage of this definition is that it's very general, and we will shortly show some interesting examples. So to appreciate what it does for us, let's have a look at some examples. Let's say here. So for the first example, I chose the usual square power. Very nice example, very simple. So how does it work? One copy of real numbers, another copy. Now here is 0, and let's say here is -2, and -2 is sent to 4, so it's somewhere up there. And 2 is also sent to 4. So there are all kinds of things happening. 1/2 is sent to 1/4, so it goes like that. And then we ask the question, okay, are there any numbers which are actually sent to themselves? Are there any numbers which stay unchanged when we apply this function to them? And that's actually a very simple question. The answer is yes, there are such numbers. One of them is 0, obviously, and the other one is 1. So 0 is sent to itself, and 1 is sent to itself. And we have two beautiful fixed points. Nice. Let's try another example. This time I'm going to look at the function square root of x. This will actually look at the first sight as the very same example regarding the, let's say, properties. Because again, we have two copies of real numbers, but actually this time I need not worry about negative numbers. So I will cut it off at the 0. And the square root sends numbers in some way. Now it works differently. So for instance, 4 is sent to 2 and so on. And again, we ask, are there any fixed points? And the answer is the same as before. Yes, 0 and 1. And I put them here. I put them here. And we have a nice picture for it. And you might ask, okay, why am I doing two examples that look almost the same? And the answer is, we will shortly see a difference. Now, the beauty of this notion, as I said, is that it's very general. When it says function, it can be real function, which is the usual meaning, but some authors interpret function in a wider sense. They actually think of a mapping when they say function. And we could try to play this game here. Mapping, that's a general notion. You have one set, another set, and you're mapping things. You're sending them over. Now, in this case, for a fixed point to make sense, those two sets, the starting set, the target set, they have to be the same. But other than that, there is really no restriction on what you are doing and what objects you are sending. So here is an interesting example. I have a mapping here which takes functions and sends them to some other functions. And how does it do it? It simply differentiates. Now here, one has to be a little bit careful. This is our starting set, and it's a set of functions, all kinds of functions here. And they are sent to their derivatives. So the target set is also a set of functions. Now, what functions? Notice that it's not enough to take for the starting set the set of functions that have one derivative. Why not? Because the target space would have to be the same. But if you take a function that has just one derivative and you differentiate it, then the outcome does not have any derivative. So the outputs, they have one less derivative compared to the inputs. But I need the same space on each side. So this is a little trouble from calculus. This is not really a topic for this course. So let me just quickly say that one possible solution is to simply take functions that have all derivatives, derivatives of all orders. And then by differentiating, you do not spoil this property. That's a very simple setup. But for us, the interesting question is, are there any fixed points? So let's translate it into another language. Are there any functions so that when you differentiate them, you get the same thing? Functions which are resistant to differentiation. That's a good way to put it. And the answer is, of course, exponential. Now, there is an interesting psychology that I really enjoy. I enjoy teaching, among other things, because it shows how people think, and this is sometimes surprising. Usually, when I ask for a fixed point, everybody thinks of the exponential. There is another one, and it's also easy, and surprisingly, people somehow don't think of it. Yeah, it's not so easy, but of course you find that the zero function, the constant function 0, is another fixed point of the differentiation mapping. So this concept of a fixed point is something really general. Let me, as an illustration, I'm not going to work with it, but just quick illustration. You can take the set of all square matrices that are regular, and you can consider mapping, which takes a square regular matrix and sends it to its inverse. Now, does this mapping has a fixed point? Well, what do we expect? We expect the inverse to be the same as the matrix itself. Are there matrices like that? Of course, there are matrices like that. The unit matrix of some dimension, yeah, the identity matrix, it works like that, but there are more matrices. So in linear algebra or in matrix theory, they actually look at this, I think they call them involuntary matrices, matrices that work like that. So this is an interesting topic, and again, this is related to this notion of a fixed point. Okay, we have our fixed points in those examples. And that was nice, optimistic examples. But now let's have a look at another example. Phi x is equal to x plus 13. Is there a number which works in such a way that if you shift it by 13, you will get the same number? And the answer is not really. So this mapping, although it's very simple, it's a very nice linear function. It does not have fixed points. And of course, the picture is quite suggestive. This is just a shift by 13. So we cannot really expect to see any fixed points. So there may be fixed points, they may not be fixed points. Let's have a look at some interesting theory. Here is a very nice statement. Function is continuous on some closed bounded interval. That's an assumption because functions which are not continuous, they are troublesome. And it says that if the function maps specific interval into itself, then it must have a fixed point. So if this function that I have here in this picture mapped everything into the same interval, then according to this theorem, if this function is continuous, it must have a fixed point. That's interesting. Let's have a look at interpretation of fixed point from a different point of view, because we are not really used to treat functions like that, with this general picture. Instead, we prefer to look at their graphs. So how do we see fixed points in a graph of a function? Well, that's a good question. I have my function, phi x, and I'm looking for a number which if I put into the function, then the outcome will be the same. What does it mean? It means that this distance of the point that I'm looking for must be same as this distance of the image. And when you play with it, you should start seeing something. But let me help you with another point of view. When we have equality like that, we can look at the function on the left, we can look at the expression on the right and also treat it as a function. And then this equality actually tells us something about the intersection. So what we see here, the equation of a fixed point, is in fact equation describing intersection of my function phi, of the graph of the function, and a graph of the function given by the formula x, which actually is a linear function, and its graph is the diagonal, y equal to x. And this intersection should be the fixed point. Let's check. Over here, it's xf. And the intersection, it's actually something which is on the graph of phi. So over here, I can see the value of phi x. So it's here. This is phi x. But because this point lies on the diagonal, this and this distance must be the same. So this is also xf. Yeah, it's a fixed point. So that's the geometric interpretation of a fixed point. It's intersection between the graph of your function and the diagonal. And that's exactly the picture that we had for this equation when we started with it as an inspiration. So this is how I'm imagining that fixed points work for real functions. And let me go back to the theorem. The theorem says the following. I have a function, and there is some interval I, let's say that it goes from a to b. And on this interval, there is this function phi, defined and existing. And now I'm assuming that the images of all points from here again lie in this interval. So I'm going to carry over this interval here. I think that could be it. So the image also lies in this interval, which means that the graph must lie in this square. There is a regular square which has the same interval for x and y projection. So it means that these 2 points, they lie on the diagonal. That's important. Because after all, the distance is a and a, b and b. So the graph of our function is somewhere in this square, and we are asking, is this graph intersecting the diagonal? Now, if the function is not continuous, then of course it may jump over. It may jump across this diagonal. So you can see continuity is crucial. But if this graph is continuous, then it must cross the diagonal, obviously. Well, let's have a look at the value at a. The value at a could be, again, a, and we have our fixed point. Or it may be something larger. So the value may be, let's say, somewhere over here. How about the value at b? It could be b again, and we have our fixed point. Or there's no other way, it has to be lower, let's say here. Now, if you have a continuous function which is passing from here to here, then whether it wants or not, it sooner or later must cross the diagonal. And you have your fixed point. There you go. Now, of course, this picture is quite suggestive, but this is not the proof. So for the proof, we have to do a little bit of work. We are going to introduce an auxiliary function, let's say phi x minus x, and let's talk about it a little bit. What do we know about this function? First of all, this function is continuous, because it's a difference of 2 continuous functions. Namely, it's continuous on interval I, which is ab. It's a bounded interval and it's closed, and because it's bounded, a and b are numbers, not infinities. Okay? So everything works as in the theorem. And now, let's see. Because the range of this function phi is again the interval AB, it follows that phi A must be at least A, which is the argument that we made over here in this picture. The value at A cannot be lower. What does it mean? Well, it means that h at A must be, and let's think about it, we are subtracting A, so we move it to the left, and we see this is positive. Here we go. Let's have a look at the value of phi at B. Again, by our assumption, this number phi B must be also in the interval AB, so it cannot be larger, definitely. We also know that it cannot be below A, but we don't care. The important thing is that it's less than or equal to B, which is what we used here in the picture. So we are actually translating the picture into algebra. If phi B is less than or equal B, I move B to the left, and I find that HB is less than or equal to 0. So now we have a function which is continuous, function h, continuous on the interval AB, and it's greater than or equal to 0 at the left endpoint, and less than or equal to 0 at the right endpoint. And there is something which is called intermediate value theorem, IVT, and it says that there must be some number, xf, in the interval I, such that h xf is 0. But hfx being 0 simply means that phi xf is xf. And we are done. So that's actually a very simple proof of our theorem. Yeah, this is actually shaping to be a nice lecture with proofs that are easy and complete. No cheating here. Perfect. So, now we know that in many situations, functions have fixed points. But how do we find them? That's a good question. That's actually the main question of today's lecture. How do we find fixed points? And how do we do it efficiently? That's another good question. Well, there is an interesting idea. And it goes like that. We start with a specific guess. Okay, I will just say, okay, let's try some number, x0. And then I take this number and I substitute it into my function phi, and the output will be my next number, my next attempt to find a fixed point. And then I say, do I like x1? Is it a fixed point? I try it, and how do I recognize it? Well, actually, if I have a fixed point, then I have equality here between this point x0 and the point x1. If they are the same, I found my fixed point. If they are not the same, well, I apply phi to x1 again, and I get x2. And again, if x2 is equal to x1, I have a fixed point. If not, I keep going. Notice that x2 is actually phi of x0. So I'm repeatedly applying my function to my initial guess. I apply it once, twice, 3, 4, 5, 6 times, 7 times, 8 times, 13 times, 100 times, and I'm waiting to get my fixed point. Or perhaps not. We will see. Let's try some experiments. Okay, let's go to my example with x squared, the function x squared. Let's say that I try x0 equal to 1/2. This looks like a nice number. So I'm going to apply function phi to it, which is x squared. And I get x1, which is 1/4, 1/4. Okay. Now I apply phi again, and I get x2, which is 1/4 squared, which is 1/16. And I apply phi again, and I get x3, which is 1/256. And I apply phi again, and I keep going. And, well, I think it's obvious where we are heading. I hope you can see it for yourself that there is no other way. This actually goes to 0, which is my fixed point. So this crazy idea of repeated application of the function phi actually seems to work for this example. Interesting. Let's have a look over here. Square root. I start with 1/2. Then I apply the function square root, and I get 1/2. Now, how much is it? That's a good question. Then I apply another square root, and another square root, and this is where it gets, let's say, a little bit tricky, because we have to call on calculus. In calculus, the limit of such a sequence is actually investigated, and it turns out that this sequence converges to 1. which is also a fixed point of our function. So for a different function, the same starting point took us to a different fixed point. This can happen easily. There is no reason why it should work the same way. After all, we have a different function. The important thing is that we did get a fixed point using this crazy idea. This is called iteration, fixed point iteration. And the general formula is like that. To get the next guy, you simply apply your function to the current guy. Okay? I think I wrote it as an algorithm. But the question is whether it's really worth writing it as an algorithm. It's so simple. Okay? Yeah, that's where it is. Iteration, fixed point iteration. How about this guy? How about this mapping which takes functions and sends them to their derivatives? How will it work there? Well, that's an interesting question. Let's start with initial iteration, which is, let's say, x cubed plus 13. Nice function. Okay, I'm going to apply my mapping, which is actually just applying the derivative. So I apply the mapping here, and what do I get is 3x squared, and that's it. Okay, I apply my mapping again. When I apply it, I get 6x. I apply it again, I get 6. I apply it again, I get 0. I apply it again, I get 0. And obviously this goes to 0, which is a fixed point of my mapping. It even worked for such general situation. This is a mapping, abstract mapping, which sends functions to functions, and the fixed point idea, the iteration idea, actually works for it. So definitely there is something to this idea. It doesn't seem to be a blind alley. It works in many situations, or perhaps not. Let's see. Let's go back to my x square example. What happens if I start at 2? You may have been wondering about it already. So we apply, this time we're applying x squared, and we get 4. Then we apply x squared, and we get 16. Then we apply, we get 256, and you can easily see that we are going to infinity, which is not exactly the best fixed point. Now, okay, this is funny. When you square infinity, you again get infinity. So in a way, this is a fixed point, but not according to our definition. Our definition says fixed point must be something which is in the domain of your function. Infinity is not in the domain, so it's out. And this shows that there can be some trouble with convergence of this situation. But the great thing is, in all our examples, whenever we do get convergence, we also get a fixed point. And actually, this is true in general. So here comes another theorem. And this theorem says, if you have a function, this time it's a real function, we are talking with real numbers to get nice theorem, and we are defining sequence xk using the iteration that we have over here, using this formula. So we have a sequence which was generated, and if this sequence converges to some point, to some xf, and if phi is continuous, again continuity crucial, then we actually found a fixed point. Now, the square function, the square root function, the cosine function when we are at it, these are all continuous functions. So if we try this iteration and it converges, it must necessarily, according to the theorem, provide us with a fixed point. Now, how do we know that this theorem is correct? Well, we will prove it again. This should be enough. Let's see. We have a sequence xk. What do we know about it? Well, it came from this iteration. So xk plus 1 is phi xk. Now, that's an equality. In fact, that's infinitely many equalities. It's equality between two sequences. So I'm going to apply limit to each side. Limit of xk plus 1 is limit of phi xk. Can I do it? The answer is yes, if the limit makes sense, if it exists. Let's talk about it. What do I see on the left? Limit of xk plus 1. xk plus 1 as a sequence is the same sequence as xk, just the index is shifted. So graphically, I have some dots, sequence xk, and I shift it. So if there is a limit for xk, there must be also a limit for the sequence xk plus 1, and it's the same. I think there was a theorem like that in calculus. So this limit on the left is actually the same as limit of just xk. And we know that this limit exists from our assumption, and therefore also this limit exists. So we were right to do this thing. Let's have a look on the right. This is a composed situation, and for composition we had a theorem again in calculus. And the theorem said, if this function phi is continuous, then it can be pulled out of the limit in a way. Algebraically, it works like that. Instead of applying limit to phi xk, I can apply phi to the outcome of the limit. Now, we are there. Limit of xk is supposed to be some number xf, and the same number is appearing as an argument of the function phi. And therefore, this limit point xf is a fixed point. Exactly what we wanted, a small square here. So that's another neat proof. We didn't really need any deep theory for it, just few facts from calculus. Very nice. So what do we know? We know that if we have a function, then of course it maps one interval into another because it goes from real numbers to real numbers, but this is not enough. According to the theorem, we are interested in bounded intervals. This is where it gets interesting. So for some functions, you can find a bounded interval which is mapped into itself. And if you get this lucky, then definitely there will be some fixed point. Is that true for our example called cosine x? Well, that's an interesting question. We know that the outcome of the cosine is always in the interval -1, 1. So it makes sense to look at a cosine as a function which takes the interval -1, 1 and maps it into the interval -1, 1. So according to this previous theorem, this must have a fixed point, the function cosine. And this fixed point is actually the solution to our original equation. How do we find it? Well, we try to apply this iteration business, and if it converges, then it will provide us with the answer. Now, when I was young, the computers were really rare. It was difficult to get to them, but everybody had a calculator. This iteration is actually very cute because you are just repeatedly applying your function to the number that you have. So I could actually do this iteration on a calculator with cosine. You just pick some number at random, you put it into calculator and you press the button which is labeled cosine, and you get x1. And then you press the button again, and you get x2. So you just keep pressing the button, and you're looking at the numbers and asking, okay, are they going to converge somewhere? Does it look likely or not? And that's actually the whole secret. Let me mimic this with Maple. For starters, I will take, let's say, number 1. That's a nice number. I like it. And we know that the fixed point is somewhere between -1 and 1, so why don't we start at 1? Now, I take this x, and I'm going to apply cosine to it. And this will become the new x, because I want to iterate. So this looks like a mathematical equality, but it's an assignment. On the right, it's the old x, and on the left, it's the new x. And then I can just repeatedly run this line, and this simulates the process of just punching the cosine again. Okay, let's see. Forgot. Maple is trying to be smart, so it refuses to calculate numbers which can be kept precise. Okay, so I'm going to force Maple now to do it imprecisely. And cosine of 1 is 0.54. Notice, remember, 0.4. Now I will press the cosine button again on my calculator. And the next number is 0.85. So 1, 0.5, 0.8. Up, down, and up. This is interesting. So I expect the next number to be down. Let's see. 0.6. So it was 0.5, now it's 0.6, 1, 0.5, 0.8, 0.6. It's a zigzagging motion which is getting more and more narrow. Let's repeat it a few more times. So I keep pressing the button cosine on my calculator, and these numbers are getting closer and closer together, still jumping up and down. I did it already like 10 times. So this is cosine of cosine of cosine of cosine of cosine of 1. Okay? And it seems that the first decimal digit, 7, is no longer changing. And this looks hopeful because it suggests that perhaps I will have some convergence happening. And now 0.73 is no longer changing. And now 0.79 739 is no longer changing. So this really looks like a convergent sequence, the one that I'm generating here. So it seems that for cosine, this iteration business works really well, and it provided me with an approximation of my solution of this number x that I'm looking for, and I think by now the 4 decimal digits should be okay. So this looks like a good procedure, and we actually have most of this procedure supported by mathematical statements, with one key exception: convergence. The theorem says if your iteration converges, then it provides you with your fixed point. But how do we know? How do we recognize convergence? How can we arrange for convergence? That would be even better. And for that, let's revisit our example over here. Let's start with the square root of x. What do we know about the function square root of x? Well, if you put into it a number which is larger than 1, then the number will get smaller. And if you put still larger number, it gets smaller, and so on. So in this upper part, the arrows go downwards. And actually, the higher you go, the more steeply they go down. On the other hand, if you substitute a number which is between 0 and 1 into the square root, it gets larger. So here we have some arrows that go like that. Now, why is this interesting or important? Let's think a bit more about what the iteration does in this kind of a picture. So here we go. I have the starting space, I have the target space, and now I have some x0. That's my initial value which I just dreamed up, and I put it into the function phi, and it gets sent to some x1. Now, in the next stage of my iteration, I should take this x1, which I obtained from phi, and use it as an argument. So what I need to do, I need to transform this x1 back into the original space. So I have to go like that, horizontally, so to speak, to get to the same position, x1, and now I can substitute it into phi, and phi sends it over to x2. And again, then I have to transform it to the original space, and I keep going. So this iteration, fixed point iteration that we have here, this is actually something like a spiral, or let's say merry-go-round. We keep going from one space to another like that. In this direction we are using phi, and in this direction we are going horizontally. That's how the iteration looks like in our arrow picture. Now let's have a look at what's happening here. We start at some place, or let's say we started at 1/2. We started at 1/2, and when we go to the right, we go up. And then we go back horizontally, and we go up, back horizontally. So it seems that we should be going to number 1, just by looking at the arrows. And that's exactly true here. What if we start with a number which is larger than 1? Then it gets smaller by applying the square root. We return back to the original space, and we go to the right to a smaller number, and so on. So this is a spiral which, again, should lead us to number 1. And you can check if your x0 is, let's say, 2, you apply square root, and you apply square root, and you apply square root, and so on. And again, in the calculus, we learned that this is actually a convergent sequence going to 1. So this seems to work. The important thing is concentric arrows. They are forcing this merry-go-round to get to some place. How about x-square function? Well, if we take a number which is between 0 and 1, and we apply square to it, it gets smaller. So there are arrows going towards 0 here, and therefore when you start this business with 1/2, this spiral will take you to 0. This looks, reasonable, this fits with our experience. What happens if you start with a number which is larger than 1? Well, there the arrows go up. So when you are going around and around, you just fly away, and you get divergence. So this experience suggests that the cases of concentric arrows are good, and the cases of arrows which are spreading out, fanning out, are not really good. So it's all about concentration of arrows. Is the function viewed as an arrow picture concentric or spreading out? So there must be a notion which somehow captures it. And if we can develop mathematical theory about this notion, then we seem to have a good chance to succeed in identifying convergence. And that's exactly what's going to happen right now. Here we go. This is a definition of a so-called contraction or a contractive mapping. And this is actually supposed to be mapping which is like concentric, which is moving numbers closer together than they are at the start. And that's actually reflected in the inequality. So we have some interval. On this interval, we have our function phi. And now we take 2 points at the starting space. We look how far apart they are. That's the right-hand side. We move them over, and we check how far apart the outcomes are, the images. And then we want the images to be closer compared to the original points. That's the inequality here. Now notice that Q is required to be smaller than 1. That's very important. Let's have a look at a small picture. What would happen, and I think this is sort of natural, if I just put this inequality in the definition? This means that the images are always closer than the original points. Over here, I have x, I have y, and they get closer together. Phi x, phi y. But if I leave it like that, and I put, of course, this for every x, y from I, then it may happen that as I'm taking different pairs from the interval I, that the distances between images are getting closer and closer to distances between these two pairs. So this inequality may be getting softer and softer, closer and closer to equality. And because there are infinitely many pairs in any interval I, if it's non-degenerate, then I could be actually in a limit achieving equality. And if I have equality in limit, it would spoil all kinds of things. So I have to prevent this possibility that some pairs of points have almost equality. And that's why I have to introduce here another constant, a separation between this distance and this distance. I want to see real separation. I want to see real concentration by some specific amount. So this Q, it says it's the worst that can happen. That's the worst sort of like spreading out that I can see in my situation. And it definitely should be smaller than 1. Okay? So that's just a technical explanation. So here we have contraction, that's the key notion. And now comes a key theorem. It's a celebrated theorem, it's called after Banach, so it's important. When there is a name in the title, then it's an important theorem. And this is, in fact, the key theorem for the whole theory of fixed points. And you can find it even in very advanced mathematical courses. I will talk about it soon. Let's see what it says. We have an interval. And on this interval, we have a function which is contractive. Moreover, this function phi maps this interval into itself. And then there is exactly one fixed point. And it can be reached using iteration. So when we define a sequence xk using this iterative formula, then this sequence converges to our fixed point. So let's have a look at the proof. It has several parts. First of all, it says that there is a fixed point. How do we know? Well, if the function phi is a contraction, then it must be continuous on interval I. How do we know? Well, one has to prove it. This is not really difficult. You look at the definition of continuity, you will see it there. In fact, it's even uniformly continuous. There is some theory about it in calculus. So this is really not a big problem. Just to give you some idea. If a function is not continuous, then it may have a trouble typically of this sort. It can get worse even. Now, when you have a situation like that, then you have 2 points which are really close, but when you substitute, the images are far. So any type of discontinuity automatically violates this principle of concentric arrows. Okay? So I think this is not really a proper mathematical proof, but I think it makes this statement believable. So we have a continuous function, and moreover, it maps interval into itself. That's another assumption, line 2. And therefore, by previous theorem, there must be some fixed point. So we have it. Great. That's step 1. We do have a fixed point. Step 2. It says there is a unique fixed point. Just one, cannot be more, for contraction. How do we prove it? Well, let's imagine that we have 2 people, and each of them brought a fixed point with them. One says, okay, this is a fixed point. another one. This is a fixed point. And now we want to show that these two guys independently actually had to come up with the same fixed point. They cannot have two different fixed points. So let's ask about the distance between these two fixed points. Well, here is a trick. I'm going to apply the function phi to each of them, and the trick is that this is a fixed point, so xf is actually the same as phi xf. I don't have to use any specific justification, anything crazy, some facts about absolute value or anything. I am simply replacing a number by the same number just written in a different way. The same argument applies to phi x tilde. And now I look at it and I say, wait a second, phi is a contraction, so there is an inequality which goes like that. I can simply drop the phi again in exchange for q, which is less than 1. That's important. We will see it soon. Now, I have an inequality. Let's say that I take the right-hand side and I move it to the left. I subtract from each side, and I factor out this distance. So I'm getting 1 minus q times this distance is less than or equal to 0. Now, let's have a look at this. That's a distance between two numbers. This is always greater than or equal to 0. Q is less than 1. So this number is positive, a strictly positive number. If this absolute value were positive also, then positive times positive yields a positive number, which is in contradiction with this inequality. So the only way to make this inequality work is to have the distance between these two guys equal to 0, so they are actually the same. End of step 2. We just proved uniqueness. Perhaps I should put the conclusion somewhere. It's an important part of the proof. That's what we wanted. So, it seems that no matter what you do, there is just one fixed point, and we are finally getting to the stage where we simply pick some initial number, some initial guess, and we generate the sequence xk plus 1 and so on using the familiar formula, using our fixed point iteration, and now we have to show that this actually converges to xf. And I will do it by essentially deriving the left inequality, the left estimate, and then I will look at it. So, how much is xf minus xk? I will just use a slightly different notation because it will make my life a little bit easier. Well, let's have a look at it. xf can be replaced with phi xf. We talked about it earlier. This is a fixed point. We know it now. xf is a fixed point, unique one. xk, by definition, is phi xk minus 1. Now, because I have a contraction, I can use inequality with q and drop the function phi. xf minus xk minus 1. So that's exactly the type of inequality I had been interested in. I just shifted the index by 1, and you will see the reason why. Because once I have this inequality, I can continue by induction. So, assuming that this number, this index, is not 0, which it could be, so assuming that it's not 0, I can again apply phi to each and so on. I simply recycle this inequality, and I get q squared xf minus xk minus 2. And then I keep going like that. How many times can I afford to do it? And the answer is essentially k times. And this requires a little bit of thinking, not too much. And after you repeat this k times, you get to x naught. For instance, if k is equal to 1, then after one step you get to to x 0, and you have 1q here. Okay, so this all fits nicely. So, I have a nice inequality here. On the right, I have an upper bound for this number, which is actually the error of approximation. Remember, I have my fixed point, I'm trying to approximate it, and I found that this, which is the error, because we can see the difference between the actual value and my approximate value, the error is bounded by q to power k times the initial error. Now, what do we know about q? Q is less than 1. It's a positive number smaller than 1. So in absolute value, q is definitely less than 1. And therefore, this, as a geometric sequence, goes to 0. So the error goes to 0. There you go. This shows that my sequence converges because the error goes to 0. xk converges to xf. And that's the most important part of this theorem, that iteration actually works for contractions. There is another inequality, which is essentially just out of curiosity. It's proved by doing the first step and then playing with it a little bit. Not too crucial. What it shows, by the way, is that on the left, we still have this error. And on the right, we are just using the latest 2 iterations. So the information on the right, that's something that we know from our run. And if we also know q, then we can actually estimate our error and stop in time. So this is nice, but actually in applications, we very often do not know q. And then there is a trouble. Okay? So the Banach fixed point theorem is crucial for this whole theory because it says once you have a contraction, everything works perfectly. And you can even choose x0 in any way. You just start somewhere in the interval, and your iteration will work. By the way, when you look at the comparison of errors, this is the error for the kth step, this is the error for the k minus first step, you get this. Let me shift the index again so that it looks familiar. This actually shows that the fixed point iteration is a method of order 1, which is not exactly all that great, by the way. But we will soon talk about ways to fix it, to speed it up. So this is actually not so bad. The main advantage of the fixed point approach is that it can be used in general settings. This Banach fixed point theorem is also true not just for numbers, but also in other sets, in other spaces. For instance, we had this example of a mapping which was differentiating functions. We talked about its fixed points here and so on. Well, actually, you can introduce the notion of a distance between 2 functions. And once you have the notion of a distance, you can start talking about contractions. So you can ask whether this differentiation map is a contraction or not. And if it turns out that it's a contraction, then by the Banach's fixed point theorem, actually, you get the existence of the fixed point and you get this iteration working because the Banach's fixed point theorem can be proved to be valid for any space in which you can measure distance reasonably well. So this is an extremely general and extremely powerful theorem. But we will not really look into it here because we are interested just in real numbers. Okay? Talking about real numbers, we have real functions. How do we recognize whether they are or they are not contractions? That's a practical question. Somebody gives a formula. Do we really want to do estimations like that, comparing, trying to figure it out? Of course not. So what to do instead, you look at the requirement with Q here, and you rewrite it in a different way. What do I want? Well, I want phi x minus phi y divided by x minus y to be less than or equal to q. That's what I want. And I also want q to be less than 1. When I look at the left-hand side, of course I have a feeling of déjà vu. I saw this one before. Of course, it reminds me of the mean value theorem. So we know that there must be some psi, traditionally written, which if I substitute it into the derivative, it will give me exactly this ratio. So this is what I want. It's not equivalent, by the way. It may happen that I do have a contraction, but for instance, it need not have any derivative at all. This can happen. So the information doesn't flow this way. It floats this way. If I have a function and I find that the derivative is bounded by some number smaller than 1, then using the mean value theorem, it follows that all these ratios also have to have this bound. So the information flows in this direction, and that's exactly the direction that I want. Because for me, it's much easier to investigate the derivative than investigating some ratios. Let's put it up. So this is a theorem which essentially follows just from calculus. And the proof is more or less here, and that's what we are going to be using. Let's go back to the Banach fixed point theorem and apply it to our motivational example. Cosine x is equal to x. So we're looking for a fixed point of the function cosine, and we found it. Let's support it theoretically. First of all, we need some interval which the function cosine sends to itself, and we talked about it. The natural candidate is the interval -1, 1, which is sent to -1, 1. So far, so good. So we have interval I, which is sent to itself. Then we have to also show that the function phi, cosine, is a contraction there. So let's ask about the derivative of cosine. How does it look like? Well, the derivative is sine of x. And we are interested in the magnitude. What do we know about sine of x on the interval -1, 1? That's the key, -1, 1. Well, on interval -1, 1, and this is a little bit important, so let's think about it for a second. How much is 1? Is it more or less than pi over 2? Pi is 3 point something, pi over 2 is something like 1.6 whatever. So 1 is definitely smaller than pi over 2, which is somewhere over here. And how does the function sine look like? It's equal to 1 here at pi over 2, then it goes down, and like that symmetrically. And because it's an increasing function, when we put it in absolute value, it becomes like that. We can claim that sine of x in absolute value is definitely bounded from above by sine at 1. And from the picture, it is obvious that sine at 1, that will be our q, is less than 1. So we do have a contraction. The function cosine is a contraction on the interval -1, 1, and therefore, according to the Banach fixed point theorem, our business with iteration will definitely work. And it did work. So this theorem is the main tool for the fixed point iteration. And as a theoretical tool, it's wonderful. But there are some, let's say, practical complications. First of all, when somebody gives you a function and it's not really friendly, then it may be difficult to establish an interval which is going to be sent to itself. For a complicated formula, it's not easy to analyze what's happening to intervals when you're applying this function to them. So that's one practical problem. And in such a case, we very often use just an inspiration from this contraction business for local information. We know from this that actually flat functions are good for iteration. Because small first derivative, it means the function is flat. It may be increasing slightly, decreasing slightly, but not too fast. That's the whole idea. So the general message is that we like flat functions. But the problem is, once we start playing with it locally, we can no longer rely on Banach fixed point theorem formally. So the information that we get is not guaranteed. Rather, it's advisory. We will see this in examples. The second thing is, or the second factor to keep in mind is that the Banach's fixed point theorem is just an implication. So there are also other situations when the iteration works, even if the function is not in contraction. So it's not exhaustive. If we just focus on Banach's fixed point theorem, we may be missing on some other good cases. A lot depends on configuration. So let me show 4 typical examples of what can happen, and we will see it better. Let's start with the square root example. So here's the diagonal, a very important feature, and here is the square root function. But for now, I will actually not worry too much. Now, our first task is to actually develop understanding of what the iteration does in this type of a picture. Now, we talked about interpretation of this fixed point iteration in the arrow picture, that we are going like that, a merry-go-round. How do we see iteration in the graph picture? Well, here we go. We have 2 spaces, x and y. This is the starting space, this is the target space, and now we choose x0, so let's say that it's here. We have to find x1 by substituting this into phi, which we do just by looking it up like that. We go vertically up, and we find x1. So far, so good. But now we have to take this x1 and transform it into the x space so that we can use it again as an argument. How do we get this number here? We need to find the same distance to get to x1. Well, there is actually a trick. We are going to use the diagonal, y is equal to x, to use mirroring to transform this distance here. And we do it like that. From the point on the graph, we moved to the left to get to the y-axis and find x1. But now we go back to the right, all the way to the diagonal, and then move down. And because this diagonal creates symmetric shapes, this distance and this distance, they must be the same. So really, x1 is now determined by going through the diagonal. Okay, we're sitting here. What do we do next? We have to substitute x1 into phi. So we go up again, all the way to the graph, and then we go left, and we get x2. But then we have to transform x2 to the x-axis. So we go to the right again, all the way to the diagonal, and then we go down to get x2. And then we substitute x2, so we go up again, all the way to the graph, left, right, and so on. Now you can see that some of the journeys were actually useless. They were not contributing. Here we were going left and right again. Here we were going down and up again. Left, right again, down, up again. All these journeys which are outside of this shape were useless. We can just focus on the movement inside this shape. We were going up to the graph, to the right on the diagonal. Up to the graph, to the right to the diagonal. So the substance of iteration, as I see it in the graph picture, is like that. You go up to the graph of phi, and you go left or right, depends on the situation, to diagonal. And this is the geometric interpretation of our iteration. And it works. Let's have a look at it. What happens if the starting point for iteration is here? This may be also x0. You go up to phi, which will lead you over here, and then you go horizontally to the diagonal. And this is actually a shortcut for two trips. One of them is here to get x1, and then you go to the diagonal and back to get x1, to this position. So here is x1, then you go vertically to the graph of phi, and you notice that it's not up but down. So this is really vertical movement. This is key. Vertical movement to phi, horizontal to diagonal. Horizontal to diagonal, vertical to phi. Horizontal to the diagonal, vertical to phi. And you can see that we have convergence also here if we start on the right. So from this picture, it seems that the function square root of x is very kind to iteration, because it doesn't matter where we start, we eventually, in this zigzagging motion, get to the fixed point, which is over here, xf. And we actually saw this in the arrow picture. They were concentric, all pointing to fixed point, which is 1 actually. So that's the situation for the square root. Let's compare it with the situation for x squared. Here is the diagonal, and here is x squared. How does it work here? Well, we choose some starting value, x0. Actually, this is not the right place for it, x0. And then we are supposed to go vertically to the graph of our function, and then horizontally to the diagonal. Then we are supposed to go vertically to the graph of our function, so we go downwards, and horizontally to the diagonal, and so on. And it seems that we are converging to 0, and that was exactly the case in our experiments. If we started between 0 and 1, here is 1, the fixed point, then iteration seemed to be going well. Now, let's have a look at it. The iteration is going well in the places where our function is flat. Also here the function is flat. So flatness seems like a good idea. What happens if we start iterating at a place where the function is not flat, where it's steep? Well, if we start here, then we go up to the graph, then we go horizontally to the diagonal, up to the graph. Well, there must be a way here, then to the diagonal, then up to the graph, and so on. You can see the divergence easily. Okay? So let's say if I start somewhere closer, then perhaps I can make a few steps here that are visible. So let's say that I start here, and this will be x1. So up, horizontally, and so on. So this shows that when the function is really steep, then we are in trouble. And this actually works also for decreasing functions. These were increasing functions of different flatness. Let's have a look at a decreasing example. For a decreasing example, I can actually borrow our motivational example over here, cosine function. That's a nice function. So how will it work here? Cosine is relatively flat, around 1. That's the function cosine. But it need not be cosine, just any function which is decreasing and relatively flat. Well, okay, we will pretend that this is still decreasing, but with horizontal tangent line. What happens if I start with, well, over here? Picture will be better here. If I start over here. Well, I have to substitute into my function, which brings me here. And then I have to find the value and use the diagonal to transform it to the x-axis. So I go horizontally to the diagonal, and this will be my x1. Then I go vertically, because I'm substituting into phi, I go to cosine, which is up here. And again, I go to the y-axis, and then using the diagonal, I transform. So I'm going to the right, in fact, to the diagonal, and this will be x2. It seems that my journey is getting closer and closer to the fixed point, but notice that this time I'm not going monotonically. Here x0, x1, x2 was increasing. Here it was decreasing. Here it was decreasing. But here I'm jumping left and right of the fixed point. And this is typical for decreasing functions. So when the function is increasing, the sequence which you generate will be monotone. When the function is decreasing, it will be alternating around the fixed point. So that's an interesting observation. Now, generally, we like monotone sequences, but when it comes to convergence and to estimating what's happening, actually this alternating business is, let's say, more interesting because you can see where it goes much better. So when phi is decreasing, you get alternating. And we also saw that when phi is flat, then you get perhaps convergence, and when phi is steep, you get perhaps divergence. This is for sure, this is most likely, okay? We cannot rely on that completely. We will see soon. So that was the case for cosine. We got this nice jumping left and right of our approximations. This is exactly what we saw in Maple when I was playing, pretending to be a calculator. Okay? And you can see that graphically, instead of a stair, which we can see over here, so instead of stairs, we have something like a spiral, which is winding inside inwards towards the fixed point. What happens if you have a function which is decreasing and steep? So that's the last case. A steep decreasing function could be going somewhere. Okay, is it steep? I guess so. So let's have a look at the situation, and quite frankly, I may have overdone it. So yeah, okay, let's see what happens. x0, just to the right of the fixed point. I go up to the graph, and I end up here. Then I go horizontally to the diagonal. So that's the first true step. The step from x0 is always preparatory, but afterwards I just move in my graph. Okay, horizontally to the diagonal, vertically to phi. Horizontally to the diagonal, vertically to phi. Horizontally to the diagonal, vertically to phi. Horizontally to the diagonal, vertically to phi, horizontally to the diagonal. Well, you can see the message. Again, there is a spiral happening here, but it's unwinding. It's going away from the fixed point because the function phi, which is over here and over here, is steep. So this really seems to fit with the general picture that we have with the general feeling. The Banach contraction theorem or the Banach fixed point theorem says if you have a contraction, if your function is flat, you can expect nice things. So actually this line is okay, more or less, based on the Banach's fixed point theorem. This line is not quite 100% true because square root example. Notice that the graph of the function square root is quite steep over here. In fact, the derivative is approaching infinity. But still, on the range between 0 and any number you care to use, you can start anywhere here, and the iteration will always take you to the fixed point 1, unless you start at 0, and then the iteration gives you 0. Okay? So over here, in this area, iteration actually also works and leads you to fixed point, even though the function is not flat here and it's not a contraction here. Definitely not. So this is a nice example that the configuration plays an equally important role as the, let's say, geometric properties of the graph. Okay. So this makes this whole fixed point business a little bit more challenging, because you don't have just one tool, but one has to sort of look at situations, think about it, and essentially what you can simply do, you try it. When you have a situation that you do not see, you try iteration, and if it works, you say, okay, great. I don't have to worry why it works. I'm just happy that it worked. Okay? So that's the general setup. And that's essentially it regarding the fixed point iteration. We have the whole theory done, and we have some interesting examples, and we have a very good insight into what's happening. Now, let's pass to another good question. Can we somehow make this iteration go faster? Let's erase the blackboard. We start by returning to our inspirational example with cosine. Let me just recall the basic situation. So the blue curve, that's the cosine function. The red curve, that's the diagonal. We are looking for the intersection. That's the solution of our equation, but also the fixed point location. And we can try the fixed point iteration. And this is the run that I did by hand when I was pretending to be a calculator. But of course, the procedure can do it too. Here I decided to start at 0. But the next x1 is already 1, and that's what I did by hand over here. And we can see the oscillating values of x. They are jumping around. Eventually, we get some approximation of the fixed point. Now, just for comparison, let's try to rewrite this as a root question. I will talk about it later, and apply the Newton method to it. And we get the answer in just 4 iterations. Now, we are not really surprised, because when we were estimating in the proof of the Banach's fixed point theorem, estimating the relationship of errors, we actually saw that the fixed point method, the iteration, is a method of order 1. So this weak performance is actually fairly expected. But can we do better? Can we somehow tweak this iteration to provide us with a faster convergence? Here we go. Inspiration. We are trying to solve this equation using the fixed point approach, and we prefer flat functions. And actually it turns out that when the function is flatter, then it's contracting more. It follows from this mean value theorem. When the derivative is small, then also the ratio that we are investigating is very, very small. So we want really, really flat functions. How do we achieve it when we are given such an equation? Well, we can, for instance, multiply it by a very small number. So I'm multiplying by a number which is presumably small, but we will see later it will not be the case. It's definitely not 0. It's never a good idea multiplying equations by 0. So after I do that, I get a new equation. And now the function on the left, if lambda is small, has also a smaller derivative, which is what I'm aiming for. The problem is that the solution of this equation is no longer a fixed point of my function on the left, because there is this lambda interfering. So I need to do something to recover x on the right. Of course, I could cancel lambda, but that would make the whole business pointless. So instead, I'm going to add a part which is missing here in a way. So I'm adding 1 minus lambda times x. And when I do, on the left, lambda phi x plus 1 minus lambda x is equal to, and when I put 1 minus lambda x multiply out, lambda x cancels, and I get just x. So the original equation is equivalent to this equation, where on the left I have a new function, and I can look for its fixed point, applying iteration, and so on. I'm back in business with a new function, phi lambda x. Let me emphasize the formula for phi lambda. So it's based on phi, and then there is an extra part. Notice that these two coefficients, they are actually adding up to 1. So this is a weighted average of 2 functions. One of them is the original function, and the other one is the diagonal function. How does the iteration look like? From this, we get xk plus 1 is equal to lambda phi xk plus 1 minus lambda times xk. And again, I can view this as an average of two sequences now. There are two sequences being connected together using weighted average. Now the first sequence, phi xk, with a bit of luck will be convergent, and then it goes to the fixed point. So this part of my formula is taking care of the business that the outcome will be what I want it to be. The second part, xk is actually a sequence which is definitely converging to itself. I'm just turning xk plus 1 into xk. Notice that if lambda is 0, then I get 1 here, and xk plus 1 is equal to xk. That's a perfectly convergent sequence because it's a constant sequence. So this is a part which takes care of convergence. And now, this lambda allows me to distribute my faith in a way. If I like the original convergence, which I get from the original fixed point situation, then I can actually even make lambda larger than 1, and then this becomes negative, and this is not a problem, to strengthen the convergence which I already have. On the other hand, if I try iteration with this phi, and I don't quite like it, because the convergence is bad, it's slow, or perhaps there is even some divergence, then I can put less weight over here, and I put more weight to this factor, which strengthens the convergence tendency. So I choose my lambda basically based on the fact how far I trust my phi. There is another interesting point of view. This can be also seen as a compromise between two graphs. I can look at it not as functions, but as graphs of functions graphically. So this new function has a graph which is an average or compromise between the graph of phi and the graph of x, the diagonal. And I'm trying to pick lambda in such a way that this resulting graph is as flat as possible. That's also another interesting viewpoint. Let's have a look at some pictures. Now, this picture shows the graph of cosine in dark blue. That's the one which starts on the top and goes down. And it's not too steep. It's flat enough to give us convergence. We saw it in this example. The fixed point iteration converged for the function cosine. But it's not exactly flat. And then there is the red curve. That's the diagonal. And the 4 curves between them, these are actually weighted averages for different lambdas. The green curve, that's when lambda is 0.8. 0.8 means that I put a lot of faith into my function and just 0.2 faith into this stabilizing or converging factor. So the resulting graph is closer to cosine than to the diagonal. It makes sense. And then I start decreasing my lambda to 0.6, 0.4, 0.2, and the graph is changing. It's getting closer and closer to the diagonal graph. There must be some value of lambda, based on the picture it seems, where the graph is almost flat in the neighborhood of the fixed point. And if the graph is almost flat, then it means that iteration will work really well. It should be really, really fast. Now, just by looking at this picture, I think that the orange curve, which is not easy to see when I'm projecting it, okay, it's 1, 2, the third curve from the top, when I'm counting on the left. Okay? Or the third curve from the bottom when I'm counting it on the right. So that's a curve which seems to be almost horizontal when it passes the fixed point, and this orange curve corresponds to lambda equal to 0.6. So let's keep this in mind. 0.6 seems to be a value for lambda that makes the graph of the resulting function of this combined function sort of flattish around the fixed point. Now, let's have a look at the code here. Here lambda is equal to 1. When lambda is equal to 1, it means I'm putting all weight on phi, and actually 0 here, I'm not relaxing at all. So when I try relaxation, because this is what is called relaxation, I should have told you that. I'll return to it. So when I try it with lambda equal to 1, I'm actually just doing the fixed point approach. I'm just using the original phi. Now here in this code, I'm actually allowed to specify the iterating function. And what you can see here, that's exactly the combination that we have here. Lambda times phi and 1 minus lambda times x. That's what we can see over here. So because lambda is equal to 1, this should yield exactly the same run as before, which took 18 iterations to actually get us to the answer. So let's have a look at it. Here we go, 18 iterations, that's exactly the same run. Now, let's decrease lambda to 0.8, which is one of the curves that we saw above. And suddenly we are just down to 7 iterations, because we made the graph flatter. What happens if I put it down to 0.6? And we are at 4. How fast was Newton? Let's go back. Newton also needed 4 iterations. So by making our function flatter, we actually achieved the performance of the Newton method, which is wonderful. Notice that for this iteration, we do not need any derivative, which brings us to another topic. This is an interesting alternative because we do not have to differentiate to do the iteration. We are just substituting to the function. Okay, let's try to move still closer to 0. So we are strengthening convergence. And things are getting worse again. So it seems that between 0.4 and 0.8, there lies some optimal value for lambda, which makes convergence really fastest. How about 0.5, 0.7, 0.6? So 0.6, if I just want to play with one decimal digit, 0.6 seems to be the best. I don't feel like testing 0.62, 0.64, and so on. This is already wonderful. This is the performance of Newton method of order 2. So this whole business is called relaxation, and this lambda is called relaxation factor. So what this proves is that sometimes it's good to relax. And this is a very important advice for life. Don't stress yourself out. Sometimes you just relax, and things will go really well. I think I put a slide here. Yeah, because this is really important. So relaxation. Relaxation for a fixed point iteration means that you simply use the formula with some lambda which you choose, and you get the outcome. And before we move on, let's go back to my example. Okay, so I tried relaxation. I tried iteration without any relaxation, and in 18 iterations I got my answer. And then I did some experiments with lambda. Good question. Why did I do those experiments if I already had my answer? So I was actually just wasting time. Well, okay, I was illustrating the relaxation point, but let's have a look at it as a problem from real life. Somebody gives you a problem to solve, you apply iteration, you get the answer. Okay, it took a while, but yeah, you have the answer. So why would you try it again and again and again? Well, 2 reasons. First, one of them. Sometimes it happens that they are solving problems that are very similar. They're of similar nature, and there are just some little details tweaked. So you solve it once, and then you solve it again with little modification, again with a little modification. And in such a case, it makes sense to assume that essentially, because these problems are very similar, that they have similar properties. In particular, if you identify some relaxing factor which works really well for this type of a problem, it will also work for a similar problem, and so on. So every time you are doing one run of this problem, of one, let's say, variation of mutation of this problem, you try different lambda. Once you try with lambda equal to 1 without relaxation at all, and you see how long it takes. And the next time they bring you this problem, but with tiny change, you try lambda equal to 0.8. And you see, okay, is it better or not? And the next time, and so on. So after you solve this problem about 5 times in different slight variations, you may end up with actually being able to solve it 10 times faster. So this definitely pays. So that's one aspect. The second aspect is that sometimes you can actually determine better lambda using analytic tools. So let's have a look at it. Here's our situation. We have a function on a neighborhood of a fixed point. And typically, we can actually narrow down the fixed point using, let's say, something like a bisection method. Notice that we are comparing 2 expressions. So we can start substituting different x's and compare these 2 numbers. Which one of them is higher, which one of them is lower? And if you get to the situation where x is higher and phi x lower, and then here it's the other way around, then for a continuous function, these 2 curves must cross somewhere. And therefore, when you exchange positions like that, you are pretty sure that your fixed point is somewhere in the middle. It's bracketing again. Bracketing just applied in a different setting. So you can actually narrow down your fixed point in this way by experimenting. And then also it allows you to choose your x0 reasonably close. Now, if you get lucky, you can identify some interval which is sent to itself, and you can apply the Banach fixed point theorem, but typically this is difficult. So what you do instead, you're looking at the derivative of your function, and you're asking, is it small here? Well, being small here locally does not guarantee anything, but it's a good hint. And if you find that the derivative is small, you try iteration, and you say, okay, I have a good chance that it will work. If the iteration doesn't work, or if you simply don't like the derivative because it's too large, you may start thinking of using relaxation. So you are using function phi lambda x is equal to lambda phi x plus 1 minus lambda x. Now, what is your requirement? Your requirement is that this function is as flat as possible. Well, the flattest function is the function which has derivative equal to 0. But the key question is where? And essentially, you want this derivative to be equal to 0 at the fixed point, but you don't know that. So close to fixed point, which you also often don't know quite precisely, but you know when you are doing those iterations. You start somewhere, so at least you can ask for the iterating function to be flat where you start. That's a good beginning. So let's put x0 here. That's a good requirement. Let's substitute into the formula. So I want the derivative of this, which means I have to differentiate here. And I get lambda phi derivative at x plus 1 minus lambda times derivative of this, which is 1. This is supposed to be 0. And this is supposed to be 0 when I substitute x0 into it. And that's an equation where phi derivative x0 is something which presumably I know because I know the function phi. And if it's differentiable, this is okay. And I can solve this for lambda. Let me see, how do I want to play it? I think I will multiply out, and I will keep 1 on the left, and everything else will go to the right. So there will be lambda here, minus lambda phi prime x0. And this allows me to deduce formula. Lambda, which is optimal, but optimal around x0. This is important to remember. This is local optimization. Optimal lambda is 1 over 1 minus phi derivative x0. And therefore, you can actually, ahead of your experiments, already figure out a good lambda. Let's have a look at our cosine example. So we have an equation, cosine x is equal to x. Let's have a look at the relaxed iteration. It uses the formula phi lambda x is equal to lambda cosine x plus 1 minus lambda x. So the formula for iteration goes like that. xk plus 1 is lambda cosine xk plus 1 minus lambda xk. And if I know lambda, I can even do it by hand if, well, perhaps not this one because of the cosine, but sometimes you can do iteration like that by hand. Now I'm asking, what is the best optimal lambda? Well, lambda optimal is 1 divided by 1 minus, and let's see, what's the derivative of cosine? It's minus sine. So it's plus sine of x0. That's the optimal lambda around x0. Now, what is our x0? Well, originally I was using 1 when I was doing the run by hand, but now for the procedure I used initial value 0, and you can actually see why. Because I can substitute 0 into sine. So for x0 is equal to 0, lambda optimal is sine of 0 is 0, it's 1. Well, this does not look exactly like optimal lambda for me, because we got a totally different result when we tried experimenting. Well, the reason is that this lambda is optimal only around 0, but our iteration moves elsewhere really quickly. From 0, we move to something like 0.7. So let's say that you do 1 or 2 steps of iteration. This looks like a good idea. You try few first steps, and optimistically you feel that after, let's say, x2 stage, you are closer to the fixed point, and perhaps now you can finally determine your lambda. So for x naught being, well, let's say 0.7, okay? 0.7 seems like a good guess after the first few iterations. How much is lambda optimal? Well, I don't know how much is sine of 0.7, okay? I mean, this is understandable. So what I'm going to do, I'm going to get some room here. Let's see. And I am going to calculate how much is, so I want to evaluate, I want the answer not as an algebraic formula, but as a decimal number. I'm asking for 1 divided by 1 plus sine of 0.7. Now, did I type it right? Yes. And the answer is it's about 0.61. So, let's go back to my run over here. I tried 0.6 and I got 4 iterations. I tried 0.61 and I get 4 iterations. And this is the picture, by the way. The blue curve is the cosine function and the green curve is the graph of this function with lambda equal 0.61. It really seems flat around the fixed point. Okay, so it all fits together. Okay, if I wanted to play really hard, I would look at the estimate of the root, which is 0.739, and I try to put it here, 0.739, and I get, again, something like 0.6. So you can see that we are close to the optimal lambda, and it actually works for even for 0.7. It's not bad, it's not bad. So the moral of the story is that information, unless you are using the Banach fixed point theorem, when you have those intervals and things like that, you play it locally, and you have to be careful about it. You have to be careful about the fact that your iteration may move to another place, and perhaps you should analyze it again. But you can actually use analysis sometimes to optimize your lambda, and then you get really fast runs. If your function is so complicated that you cannot figure it out analytically, or if your function does not have a derivative, for instance, because you are not given a formula but values, then you can try to find lambda by repeated runs experimentally, as I've been talking about it. Now, let's have a look at something. You start with x0, you get x1, and you determine optimal lambda for it. You do iteration. With this lambda 1, you get x2, and you determine optimal lambda 2, and so on. So you get lambda k for xk at each stage. So if this calculation is not too crazy, if it's just a simple formula, you can actually afford to incorporate it into your fixed point iteration, and you can update lambda, the optimal lambda at each stage, and this should be super fast. Now, to see why is this interesting, let's erase this and let's have a look at it again from a different point of view. Here is the situation. You are trying to solve an algebraic equation, and they actually prepared it for you so that you can apply the root finding methods. Newton method, secant method, bisection, and so on. But for some reason, you do not feel like this, so you would like to use the fixed point approach using the fixed point iteration. Now, an equation is just some algebraic expressions, and you can rearrange it in many ways so that x appears isolated on one side. However, if you want to develop some theory, we have to settle on some standard procedure and work with that. And it's traditional to get the right type of equation in the easiest possible way, simply by getting plus x on each side. So on the left, we have fx plus x, and on the right, we have x. And this is our phi. So that's the standard transformation of a root problem into a fixed point problem. And this standard transformation has the advantage that we can do it always, and disadvantage that it almost never works. But it's another story. We will get to it. By the way, some authors, before they add x to each side, they multiply this whole equation by minus. So here on the left, they have x minus fx as an alternative phi. Which one is better? The answer is none of them. For different functions, this works better or the other works better. Yeah, it's a toss-up. essentially. So I like the simplicity, I keep it like that. Some authors, they use x minus fx because it has some minor advantages at some moments. Okay, let's stick with this one. So I have my root problem. I transformed it into a fixed point problem, and now I want to apply relaxation. So what is the relaxation formula? I have to take my original fixed point function and multiply it by lambda. And then I add 1 minus lambda times x. I multiply out, and I get lambda fx plus lambda x minus lambda x. So that's it. It becomes very nice. So this general theory that we are trying to develop here leads us to this nice formula. So that's the relaxed iterating function if we start with the root finding problem. There is an interesting alternative way to get to the same place. Here is my motivation. I want to introduce factor lambda. So I take this original equation and I just multiply it by lambda, and I get lambda fx is equal to 0, and then I add x. And I get lambda fx plus x is equal to x, and this is my phi lambda. Okay? So that's just an aside that you can get to the same place in two different ways. Now, let's assume that we did some iterations and we have already point xk, and we decide to optimize our relaxation. So what would be the optimal factor lambda for xk? Well, we have a formula somewhere here. I preserved it. So we are getting 1 over 1 minus, and now we should take derivative of phi and substitute xk after we are done with this derivative. I hope you know the notation. This is delayed substitution. Okay, how much is it? 1 over 1 minus, and I differentiate, and I get f derivative xk, and here derivative of x is 1. And this is in brackets, like that. So I just differentiate it, and I substituted xk, and now I look at it and I say, wait a second, 1 cancels, and I'm getting minus 1 over f prime xk. That's the optimal lambda if I decide to follow the standard transformation from a root problem to fixed point problem. Now I'm applying iteration, fixed point iteration, with optimized lambda, which corresponds to xk. So I'm optimizing at every stage. How does it work? xk plus 1 is phi lambda k xk. I'm using the relaxed formula with optimized lambda. So I should take the optimal lambda, which is negative 1 over f prime xk, multiply it by fxk, and add xk. And when I look at it again, I see that I'm taking xk and subtracting fxk over f prime xk. And this is the Newton method. So the Newton method is in fact something like a fixed point, standard fixed point approach, which was optimized at every stage. Which is another explanation why it is so fast, because it's optimized locally. That's a very interesting coincidence. Two different viewpoints, and we end up with the same idea for a very super fast method. However, before we start praising it too much, notice that I said this is for the standard transformation. We add x and so on. There may be other transformations, and they may actually beat the Newton speed even without any relaxation. It all depends how you create this function phi. So again, this fixed point approach is interesting because you don't go by numbers. You don't have a strict way which you follow and you get it. You have to think, you have to experiment, you have to look at what you are doing. This is very nice. So we covered now all the theory, all the interesting aspects, and it's time to do some experimentation. In this chapter, whenever we introduce some new method, we always use this cubic equation to test it. And we will continue in this tradition. let's first narrow down or bracket the point that we're looking for. So this is the root point of view, and I can try to substitute in some numbers into f. If I substitute 1, I get -8, which is negative. And if I substitute, let's say, 3, I expect this to be positive because the cubic power is really, really fast. So 3 cubed is 27, plus 3 is 30, which is a nice number, minus 10 is 20, which is also a nice number, and it's positive. Okay, so now we know that the number that we're looking for is in the range between 1 and 3. So x, it will be the fixed point later on, is in the interval 1 and 3. By the way, the solution is actually 2. We know it, but we will pretend that we do not know it. But it will give us something to look forward to. And for the starting iteration point, we can take 1 because it's reasonably close to the root, which is somewhere here in between. Okay, so that's the situation. Also, let me recall the formula for the relaxed iteration looks like this. And the formula for the optimal lambda is 1 over 1 minus f prime x naught. That's it. So that's the playground for essentially the remaining part of this lecture. Let's play with the fixed point approach. As the first attempt, we will try the standard approach. So I take this equation and I add x to each side. And I get x cubed plus 2x minus 10 is equal to x. So this is standard. And let's see how it works. So what we have over here is our iterative function phi, x cubed plus 2x minus 10. And let's see what do we think about our chances for convergence. Now, ideally, we would test the Banach's fixed point theorem. And for that, we would have to identify some interval which is transformed into the same interval using this cubic polynomial. Now, this is not really easy to find, if it exists at all. So we will skip this, unfortunately, but this is typical. And instead, we will just get some advice on the flatness. So what do we know about the derivative? Derivative is 3x squared plus 2. And this is definitely at least 2 on this range that we are interested in. So this is bad. It means that the derivative is significantly larger than 1. Significantly, it's even more than 2, so it's not even close. So I'm pessimistic. I don't think this will work. So here we go. Here is my function. And just to get some comparison, the Newton method can find the root in 5 iterations, which is perhaps also an interesting information. So Newton, 5 iterations. Now, if I try the standard iteration, fixed point theorem iteration, I can actually just call on my procedure. And after 3 iterations, that was really quick, after 3 iterations, the procedure refused to work anymore because it says the numbers in iteration are too large. That's another check. There are essentially 2 checks. I've been talking about one of them. If there are too many iterations, the default says 50, but I can extend it. If there are too many iterations, the procedure stops and says, hey, look at it. There may be some trouble. Another check is about numbers. If they grow larger than 1 million, and you can also change it in this procedure, if they are too large, the procedure stops because, yeah, you deserve to be warned about it. This looks really, really bad. Bad divergence. So this is what I've been talking about. I've been hinting that the standard approach, the standard transformation from a root problem to a fixed point problem is usually typically not exactly the best one. Can we improve it by relaxation? Well, we can try 2 things. We can try experimenting, or we can try to find the optimal lambda. Let's try the optimal lambda way based on our initial value 1. So we should take 1 over 1 minus. Now we should differentiate the function, and we have the derivative here, which is nice. 3x squared plus 2. And we substitute x equal to 1. 1 is the starting point. So it seems that the optimal lambda around 1, okay, 3 plus 1 is 5, negative 4, it's negative 1 over 4. This seems to be the optimal lambda. Okay, first, the standard transformation. That's my phi. And I'm just checking that the general procedure did it right. So if I choose my transformation by adding x to the left-hand side, which is the code over here, and then I use it, and I can actually specify my own phi in this procedure, which is what I did, I get the same run. That's correct. And I will try lambda equal to 1, which means I'm not doing any relaxation, and I should obtain the same run. Exactly. And now let's play. Let's decrease lambda to, let's say, 0.5. Will it help? And the answer is it helped a little bit, because it took one iteration more before the procedure gave up. So, yeah, it did help. How about 0.2? We are going in the right direction, it seems. One more iteration, okay, but still nothing great, 0.1. Now, it doesn't really make much sense to go really close to 0, because then we are losing the connection with the iteration itself. If we put 0 weight here, we don't know where the iteration should go. So, in desperation, let's try a negative number. Well, it's recommending negative 1 over 4, negative 0.25, and let's see. Well, we still ran out of room, but this time we didn't stop because of huge numbers, but because we reached the maximum allowed number of iterations. Let's have a look at the axis. Wow, we've got a cycle. This sometimes happens. Remember the picture when we are jumping from the function to the diagonal and back to the function and so on, doing all kinds of nice journeys? Sometimes it happens that you are just going in circles. So for lambda equal to negative 1 over 4, we are going in circles, which is not good. But we are not going to infinity, which is a good sign. I've been talking about it. This negative 1/4 is optimal around 1, but obviously we are moving elsewhere. So yeah, let's try to play with it a little bit. Okay, how about negative 0.2? Well, this is better. Do we still have a cycle? Well, every fourth number starts with 0.5162. Yeah, we have a cycle, but this time the cycle is longer. And it's not quite true, actually. There are subtle changes. So we are like not going in a circle, but it's a circle which is slowly moving, slowly moving. So it's a little bit better, but still not all that great. Okay. How about negative 0.1? Wow, we've got convergence. 7. 7, this is definitely nice. And it took us to 2, which is also great. And 7 iteration is not all that bad compared to Newton. Now, of course, we know that the optimal lambda is best determined at the fixed point. And normally you don't know it, but let's cheat. We know the fixed point. So lambda optimal for x equal to 2 will be 1 over 1 minus, I'm substituting 2 into this derivative. 4, 12, 14, this is negative 1 over 13, which is great. I love 13. You noticed probably already. So I really love this optimal lambda. And let's try to put it over here into my procedure. So negative 1 over 13. And we get to 5 iterations, which is matching the performance of the Newton method. So not only that we saved divergence by smart relaxation, but we actually turned the convergence into a really quick convergence, which is matching the Newton performance. And it doesn't get any better, really. If you try experimenting with the numbers, yeah, this is the best. But of course, we cheated because we knew the root. So if we didn't know the root, we would have to, let's say, try a few iterations. We see how it goes. We try to optimize by experimentation. This could be saved. But it's not the best approach, actually. We saw that when we tried without relaxation, we got divergence. Let me put it here. So the standard approach, eventually we forced it to work. We got convergence, but it took a while. Let me show the picture for this. Okay, what do we see here? The red curve, that's the diagonal, and the blue curve, that's our function phi, which we are trying to use for fixed point. So this phi, it's a cubic curve, which is growing quite fast. It seems around 2, which is the fixed point. And that's why we got this divergence. It's really steep. It's not flat by any means. Now, if I use relaxation, I am sort of like doing average between the red and the blue curve. the diagonal, our function, phi diagonal, y is equal to x. When we are using lambdas from the range between 0 and 1, it means we are taking compromises. We are taking curves from this area. And if we do it here, if we apply such lambdas here, we still get something which is very steep. So green curves which are here in this area are no good. We have to move outside, which means that we have to either make lambda larger than 1 to get closer to phi, but from the other side of this shape, or we have to take negative lambdas which take us somewhere here. So we took negative lambda and we got outside of this natural range to a flat curve. Okay? So this explains that sometimes lambdas which are non-traditional, which means negative or larger than 1, can actually make sense. All depends on the situation. Okay, the standard approach eventually worked out, but not anything great. Let's try something else. We have an equation here, and our aim is to isolate x on one side. So why don't we just leave it here and move everything else to the other side? So we will get 10 minus x cubed is x. That's our attempt number 2, using algebra with this iterating function. So the iterating formula would be xk plus 1 is 10 minus xk cubed. That's a very nice iterating formula. Does it stand any chance of convergence? Well, as an experienced, let's say, fixed point iterator, I'm mildly pessimistic because this cubic power does not seem very friendly given that I'm working with large numbers. If it was close to 0, then x cubed is flat, we know that. But when you are to the right from 1, x cubed is really steep. So I'm not very happy about it. I take the derivative in absolute value. I have to be careful. I'm taking it in absolute value. I didn't have to worry here, but I do have to worry here. So it's just 3x squared. That's the derivative in absolute value. And this is at least 3, which is more than 1, on interval 1, 3. So again, I don't see it very optimistically. Here we go. Here is my phi, but now this time my phi will be different, 10 minus x cubed. So I'm really doing custom things. This is my new iterating function, and I use it without any relaxation, and I got divergence. This is what I expected. So this phi leads to divergence. And it seems equally bad as the standard way. Now, can we fix it by relaxation? So again, let's go by experimenting. If I try 0.5, still bad. How about negative 0.5? Still bad. How about 1.5? Still bad. This looks really bad. Does it mean that it's hopeful? That's a good question. Perhaps I should try some other lambdas. Perhaps I've been too hasty. 0.8. Still bad. 0.2. Oh, it actually looks quite hopeful. Well, we seem to be cycling again, so let's move around 0.2. How about 0.25? Wow, we've got a nice cycle. How about 0.15? Another cycle, 0.1. Ah, I got convergence. So this is also, this can be saved. It's salvageable using relaxation. So for relaxation, let's have a look at the optimal lambda. It's 1 over 1 minus, and here I have to put the derivative, but without absolute value. So I take the derivative here, and I get minus 3x squared, and I substitute some point into it. So let's say that I try it around 1, which is where I'm starting. Then lambda optimal should be, okay, I'm substituting 1 here. This is 1 over 4. And 1 over 4, I tried it and it didn't work because this is optimized in a different place. So let's have a look at optimization, which is at the actual fixed point. And there lambda optimal is, well, let's see. I'm adding 3x squared, 4, 12, 13, 1 over 13. No, yes. I can't believe it. 1 over 13 again. So let's try this. This is an optimal lambda, 1 over 13. And we again match to the performance of Newton. But again, this we would know in actual real life. But by experimentation, we could perhaps save this, at least. OK, let's have a look at the picture. So this time, we are in a similar situation, but there is a difference. This time, the blue curve is actually, it's a decreasing function. Here the function was increasing, and here the function was decreasing. So we took very, very tiny lambda, and yeah, things worked out. Things worked out reasonably well. OK, let's have a look at another transformation. Where is it? My phi. So now we will try something else, because this also was not all that great. OK, I look at this equation and I ask myself, is there some other way to isolate x? Well, I took it from here. What if I take it from here? So x will be, I take these two guys and I move them to the right, 10 minus x, and then I take the cubic root. So that's my new phi. Now, taking cubic root is not a bad idea, because the cubic root is flat for larger numbers. So this looks hopeful, actually. Let me just write down the iteration again. That's the standard iteration for this function. 10 minus xk to 1 over 3. Let's have a look at our expectations. F prime x in absolute value. So I'm taking derivative, so 1/3 drops down. And then there will be 10 minus x to negative 2/3. So it will be like that. 10 minus x to 2/3. How much is it? Well, that's a good question. X ranges between roughly 1 and 3. Perhaps we may run out of this interval in our experiments. But what is the largest possible value? This is in the denominator, so I'm asking for the smallest possible value. Well, the smallest possible value for this is when x is equal to 3, and then there is something like 7 to 2 over 3. This is a large number. This is a very small number, very tiny number. I don't want to calculate. OK, 7 squared is 49, which is about 50. Cubic root of 50 is something like 3 and something. 3, I would say roughly, with quotation mark, OK, I'm just guessing. This should be less than 1 over 10, which is definitely much smaller than 1. So I'm very, very optimistic. This should work right out of the box. So I have to be careful in Maple, because Maple has some strange idea about taking cubic powers. So I have to do it like that. And it's the cubic root from 10 minus x. Here we go. Now, that was wicked. 4 iterations led me to the answer. Converges in 4 iterations. Notice that this is better than Newton, even without relaxation. So what is the moral of the story? The moral of the story is that relaxation is powerful. It can fix your iteration, but this iteration is based on a transformation which was your choice. So relaxation can work only with something that you start with. And it's your choice where you start. If you start wisely, then the relaxation has a much better starting point, and you don't even sometimes need it. Sometimes the iteration actually is so good that relaxation cannot even improve it. And I strongly suspect this is the case. But let's do some experimenting. So this shows that rather than working with relaxation and spending a lot of time on it, if it looks like that, it may be much smarter to actually simply try a different transformation of your original equation. If you don't like your transformation because the function is too steep, you simply try another formula, another rearrangement, which leads to a flat function, and you are happy. OK, let's just experiment a little bit. This is really, really quickly convergent, so I can even strengthen it. Let me put 1.1, which says I want more of this, not less. No, it doesn't work. How about 0.9? We've got down to 3 iterations. Now, this is almost half of the Newton performance. This is amazing. How about 0.8? It's already too much again. So it seems 0.9 is about the optimum. lambda optimal, when x is near 2, should be about 1 over 1 minus. Now we have to put the derivative in here, and I want to substitute 2 into it. So it's 1/3, 1 over 10 minus 2 to power 2/3. And I actually have to be careful, because this is the derivative in absolute value. That's why I didn't have to worry about signs. But now I do have to worry, because this is the derivative itself over here, without absolute value. So I take derivative. 1/3 comes down, that's okay. The power changes. Inside function, when I differentiate the inside function, there will be minus jumping out. So there will be minus here. I have to be careful, super careful. 10 minus 2, do I dare? I don't like those powers. Let's see if I'm lucky. 10 minus 2 is 8. Cubic root of 8 is 2. I am lucky. 2 squared is 4 times 3 is 12. So it's 1 over 12, which is added to 1. This is 13 over 12. So I'm getting 12 over 13. Now, this is a remarkable coincidence. Another 13 in the game. Yeah, I really like the number. Okay, let's close it off. This has been a very successful experiment. 12 over 13, this is something smaller than 1, but close to 1. So it seems that our experimental guess, 0.9, let's see over here, was more or less correct. Okay, I don't completely trust myself in this calculation, so let's ask Maple, and let's actually even ask Maple to evaluate the derivative. So lambda optimal should be 1 divided by, and now it comes 1 minus, and now we want to substitute value 2 into derivative of my phi with respect to x. Did I forget something? Let's see. I substitute, I do this, I do that. Of course, I have to end it with semicolon, and Maple actually sometimes refuses to evaluate into decimal form, so I have to force it. I think that's it. 0 point something something. So our experimental value 0.9 was most likely quite okay. And now I ask Maple to take this number and multiply it by 13. And if we get 12, then I was correct in my, oh yeah, we are getting 12. So this is optimal is really 12 over 13. In decimal numbers, this is 0.923. Let's try to put here 0.923. Okay, 3. We never get better than 3, so this is optimal. This is wickedly fast. So this is the winner so far. Even though without relaxation, 4 iterations, we put it down to 3. Wonderful. Again, let's have a look at a picture, whether we will see something new. I don't quite expect it. Well, the blue curve, that's this function phi, and you can see that it's already flat. That's why we have this wonderful performance. And by optimizing lambda, we made it slightly flatter, and we saved 1 iteration. Wonderful. Okay, this is actually a game that I enjoy. You take a formula and you start thinking, okay, where would I get some x's out of it? How can I get x from such an equation? Well, let's have a look at this idea. I can factor out x, and I get x squared plus 1 minus 10 is equal to 0. Now, what can I do with that? I have 2 sources of x. I could try to pull x from here, which would require me to take square root. Now, square root is flat around between 1 and 3. This doesn't sound like a bad idea, but square root has trouble with existence. If some negative numbers come in, this could be tricky, but it's not a blind alley. Another possibility, another venue here is to isolate this x. And that's what I will do. I will move 10 to the right. I will divide it by this expression, and this will give me x. So that's my phi. And when I'm looking at it, I sort of like the derivative and also like the shape. It's a hill-shaped curve. This looks also hopeful. So what's the derivative of this? Derivative of this, I don't feel like using the quotient rule. So instead, I imagine that it's x squared plus 1 to power negative 1 over here. And when I imagine it like that, there will be negative 10 divided by x squared plus 1 squared. So this took care of the outside derivative, and it's multiplied by 2x. So that's the derivative. And I should ask about the absolute value. And I should ask how large it is. Now let's see, how much is this number around 1? Around 1, this is 4 in the denominator and 20 in the numerator, it's 5. So the derivative at 1 is about 5 in absolute value. That's too much. I don't like it. I don't really like it. Around 3, 3, 9, 10, 100 in the denominator and 60 on the top. Phi at 3 is, did I say 60? Yeah, 6 over 10, which is 3 over 5. This is less than 1. So around 3, it's flattish. So I'm getting mixed signals. I don't really know. Okay, let's experiment. Why not? So this time I'm taking 10 and dividing it by x squared plus 1. Okay, I'm getting a cycle. Is it a perfect cycle? The answer is yes. So it's not a total divergence. It's not a total disaster. But it's not something to write home about either. But because it's so, let's say, reasonably nice, some relaxation might fix it. How about 0.9? I don't like that. How about some more intensive relaxation, 0.5? Wow. Now, talk about luck. This is the winner, absolute winner. 2 iterations. What happens if I put 6? I still get convergence. So this is a rather aggressive relaxation, 0.5. You know, I don't trust this function all that much when I'm using just half of its weight. 0.4. Decent. This is the Newton performance in 5 iterations. That's how the Newton did. But with lambda equal 0.5, wow. But we got lucky, of course. Lambda is equal 0.5, 2 iterations. So by a remarkable piece of luck, this happens to be a winner if we also consider relaxation. Otherwise, out of the box, this guy is the winner. Interesting. Let me see. Picture. So what you see here is exactly corresponding to this information. Around 1, the function is growing really steeply. That's the blue curve. Around 3, it's a little bit flattish. With the relaxation 0.5, we moved it so that it's relatively flat on the right and around the fixed point, but I do not quite see it as optimal. Perhaps there is even a better way. The fact that we jumped into the solution in 2 iterations was actually more due to algebra. We got simply lucky that we ended up at 2. If we ended up at 2.2, we would have many more cycles because substantially this iteration is slower. The green function is not totally flat. So we got really lucky due to algebra, not due to the properties of iteration. Wow, that was really wicked. Okay. How about let's try the version with square root. So I move 10 to the other side. I divide by x. I subtract 1. And then there will be just x squared left. So to get it, I take square root. And this is phi x. Do I like it? The answer is well. Let me see. If x happens to be larger than 10, then this number will be negative. So this all makes sense for x less than or equal 10. Definitely. Hopefully, I will never get that far. So this looks mildly optimistic. How about the derivative? Well. Let's see. I have to take the absolute value eventually. I take the derivative of the square root, which is 2 square roots of 10 over x minus 1. And then I have to take the derivative of the inside function, which is negative 10 over x squared. Now, how much do I like it? That's a good question. Well, what happens when x is 1? When x is 1, this is square root of 9, which is 3, so I'm dividing by 6. 10 divided by 6. This is too much. This is bad. This is more than 1, to be precise. More than 1. That's important. When x is 3, then this is 10 over 3. Ouch. Okay, let's say this is 3 minus 1. It's slightly more than 3. minus 1 is 2 and something. Square root of 2 and something, it's, let's say, 1.5 times 2 is 3. I'm dividing by 3, I'm dividing by 9, I'm dividing by 27, 10 over 27, roughly, which is smaller than 1. So again, I'm getting mixed signals. I'm getting mixed signals regarding this iteration. So, well, let's see, where is it? My phi, here. So I'm taking square root of 10 divided by x and subtracting 1. Is that the right formula? 10 over x minus 1, square root of it. Yeah. Here we go. And we got convergence, actually, out of the box. But it's convergence which is essentially rather slow. 18 iterations. So this is roughly linear convergence. And again, we could try to find optimal lambda. Do I feel like playing with this formula? Not really, I have to admit. Okay, let's try it by experimentation. So lambda 0.5, okay, it worked well. Oh, now this is unbelievable. So when we try to relax and use lambda equal 0.5, we get it in 2 iterations again. Now I said that this is due to algebra, not due to the quality. So let's try something a little bit nasty. Instead of starting at 1, I will start at 1.3 or 1.03, okay? Let's just change it a tiny little bit. And then the algebraic luck no longer applies, and we are more looking at the, let's say, qualities of the iteration, and we are to 4 iterations. So that's really the difference between the quality of your situation and algebraic luck. We just lucked into the number 2 as the answer there. This is more realistic appraisal of the qualities. So it seems that these 3 transformations, they are of about the same quality when it comes to achievable performance. All of them can get you to 4 iterations, but for these 2 you have to use relaxation. This one gives you 4 iterations right out of the box. And this one actually allows you to improve it when you do relaxation. And this improvement is really based on the quality of the function, not on luck. Wow, I haven't been that lucky in a while. So yeah, that's the general example. On a test, you will be given an equation, and I will ask you to show 2 different ways to transform it into a fixed point problem and analyze what's going to happen. So essentially, expect to see something like that. Okay? You can use the standard transformation if you want. You can use any other transformation that you can think of. You will not be expected to actually provide the calculations and check whether the thing diverges or converges. Rather, I expect you to look at the derivative on the neighborhood where you work, and you will be given the starting point. X0 will be given to you, okay? Just like here, X0 is 1, you will be given the starting point, and you will be expected to look at the derivative, how large it is, and make some conclusion. You have to justify it. You have to tell me it's more than 1, it's less than 1. You have to tell me how you decide whether the situation is optimistic or pessimistic. I don't expect you to do the full, let's say, Banach fixed point theorem investigation, because I didn't do it here either. I didn't look for interval which is mapped into itself, things like that. Too much work. So I just want you to look at local situation and make appraisal. Tell me, I see it optimistically, I see it pessimistically, and also I will ask you to show a few iterations by hand so that you can illustrate that you know what you are doing. So for instance, some nice formula. Which one do I like? Perhaps this one is nice. So if you decide to transform the equation into this way to get a fixed point problem, and I tell you that X0 is 1, then you could, by hand, substituting into this formula, figure out that X1 is 10 minus 1 cubed, so X1 is 9, and X2 will be 10 minus 9 cubed, which is a lot. So those problems which I'm preparing for you, they will be specially prepared, I have to be careful, so that you can actually do the calculations by hand. Usually I ask for 2 iterative steps. So here, well, actually you can simply write 10 minus 9 cubed. And I take it. I don't need this in any other calculation. So you can leave it like that. Yeah, that's good. It's a precise answer, although I don't see it as a number. But yeah, it's a precise answer. Okay? So
This is just to let you know what I expect from you. I definitely expect you to be able to do this calculation, and if you want some, full points, then you should also be able to do a little bit about optimization for the relaxation, to be able to set up relaxation equations, things like that. Then you get full points. You will be happy, I will be happy. And that's it regarding the chapter called Solving Unsolvable Algebraic Equations. There will be no more tricks, but there will be a bonus video